Hello, this is page 2 of the Accelerated Chemistry, Molarity, and Thermochemistry practice test. Now again, this is the dilemma about making things late at night. Sometimes you forget to include certain key parts of your problem, which I have included here. I apologize that I've had to zoom out quite a bit for this particular problem. This is going to take a lot of space, so I want to make sure that we really get a firm idea of what's going on here. What I didn't include were all of the tools you need in order to solve this problem. I included one tool, heat of combustion, you will need to know. Because in the end step, we are burning ethanol to make 2.5 kilograms of ice turn into water vapor. What you need to know is that there are 5 steps to the heating process, and then the last component is changing my heat that is required into ethanol. So it's really breaking down a big, overwhelming problem into small steps. The keys I need to do that are specific heats and molar heat of fusion and vaporization. Just to review what we've talked about before, so the specific heat of ice, we may not have seen, we're not familiar with. We are familiar with the specific heat of water. Water has an extremely high specific heat, but given the molecular interactions of water, has a higher specific heat in a liquid form than it does in a solid form or in a gaseous form. That is really vital to know, because we can't use the same 4.18 for water in every state. We can only use the 4.18 for water when it is in liquid form. I'm hoping, I might have to zoom in a tiny bit. I'm hoping that my camera's focusing as it should. Okay, so molar heat of combustion for ethanol, I don't need to worry about that right now. What I need to focus on is how much energy is required to take 2.5 kilograms of ice at negative 40 degrees Celsius into water vapor at 180 degrees Celsius. My first step, I'm starting with ice. I need to warm up ice from negative 40 degrees Celsius to 0 degrees Celsius, at which point the ice will convert into water. So this is a good old specific heat problem. What I need to find is the energy required to make this happen. So my Q value, which remember I can write Q now, change in heat. What's the heat change that's required to make this happen? It's my mass of water. Now you remember, we're dealing with kilograms, but specific heat deals with grams. So it would be 2.5 kilograms is 2,500 grams. The specific heat for ice is 2.06. And my temperature change is going from minus 40 degrees up to 0 degrees, at which point your heating curve will level off because the ice needs to turn into water, and the ice needs to absorb heat in order to turn into water, even at the same temperature. So my temperature change is 40. I have all the components I need to solve for energy in this step. So 2,500 times 2.06 times 40 equals 206,000 joules, which is the energy amount. Now, as I'm going along, realize I'm making joules, I'm dealing with joules in specific heat. However, I will need to worry about kilojoules. So it's just a smart idea right now while I'm doing this to do my unit conversion so that I cancel out my joules and I keep everything in kilojoules. That's a good idea. So it doesn't take a tremendous, enormous amount of heat to take ice and heat it up. The next step, we're taking ice at 0 degrees Celsius, we're turning it into water at 0 degrees Celsius. Because ice can exist at 0 degrees Celsius, water can exist at 0 degrees Celsius. Ice has less energy than water because ice, the molecules are not moving, at least not moving around. They may be vibrating, but they're not moving around. Water molecules are moving around. That's the characteristic of a liquid. So, this is what we call heat of fusion. For 1 mole of H2O solid, I need to add in 6.02 kilojoules of energy in order to make 1 mole of H2O liquid. Now, if we were ever to go the reverse process, this is an endothermic process. Water must absorb heat in order to become a liquid. The reverse is an exothermic process, but it's the same exact number. So the reverse of this, if I have liquid water, I need to remove 6.02 kilojoules of energy in order to turn it into a solid. So my delta H in that case of heat of solidification would be negative 6.02 kilojoules. That energy has to be released in order for water to go from a solid to a liquid. Now, at that point, we have our balanced equation. Now this becomes a stoichiometry / thermochemistry problem. I have 2,500 grams of water. I need to turn that into moles. Why? Because this is kilojoules per mole. Gram molar mass of water is 18.01 grams. I'm sorry, 18.02 grams. So, 2,500 divided by 18.02, oh boy, 2,500 divided by 18.02, 138.7 moles. Now, I'm really only going to eventually get down to 2 significant digits because I only have 2 significant digits, but can I work with this now? Sure. Especially ACCELChem, kids love big numbers. So, 138.73 moles of water. Now, for 1 mole of water, I'm required to have 6.02 kilojoules. Now I'm going to cancel out my moles. I'm going to figure out how much energy. I have my first energy here. That was taking ice at negative 40 to 0. Now I'm realizing the energy required to take 1 mole of ice and turn it into 1 mole of water. So 138.73 times 6.02 equals 835.15 kilojoules. So that is the energy required to take 138 moles of water, which is my 2.5 kilograms of water, and turn it from ice at 0 degrees Celsius into water at 0 degrees Celsius. Now, I'm going to go from water at 0 degrees Celsius to water at 100 degrees Celsius, at which point my heating curve will level off again because energy has to go into the water in order to turn it into steam or water vapor. This is now another good specific heat problem. Delta H equals mass times specific heat times change in temperature. Now, I'm going to solve for H. I'm assuming that no water at any point here turns into water vapor. Does some water turn into water vapor at any temperature? Yes, it's something called vapor pressure. We'll get to it when we talk about gases. As of now, don't consider anything significant. So in this case, we have still 2,500 grams. Now our specific heat for water is 4.18. And our change in temperature is 100. Now this is going to be a pretty substantial amount of energy because water absorbs a lot of energy in order to raise its temperature. So 2,500 times 4.18 times 100 gives me, that seems ridiculous, 2,500 times 4.18 times 100, well, what do you know? That's going to be, well, we are talking about a lot of water. So this equals 1,045,000 joules. Don't forget, we're dealing with joules here. If I convert this into kilojoules, that's 1,045 kilojoules. That's my next step in the process. So I've gone from ice at -40 to 40. I've gone to from ice to water. Now I've raised the temperature of my water. It required 1,045 kilojoules, or 1,045,000 joules, in order to raise it to that temperature. Now we have water at 100 degrees Celsius, and we go to water vapor, aka steam, at... The reason why I'm bothered by the word steam is actually truly condensation. It's water condensing as it bubbles out of solution. When the boiling water in a pot actually hits the air, it condenses again. You have tiny little droplets of steam, so it's really truly water vapor. But remember, water and water vapor at the same temperature do not have the same energy. Water is still very sticky. Water has those strong hydrogen bonds, those intermolecular forces. You've got to put a lot of energy into water in order to turn it into water vapor, because you're breaking those intermolecular forces. You're breaking those hydrogen bonds. This is why you can't forget any of this over the course of the year. This is why chemistry, one thing builds upon another. Now, heat of vaporization is my key here. We have 40.7 kilojoules per mole. Now, could I recalculate moles, 2,500 grams times 1 mole? No, but yeah, I could, but I already did it up here. I don't need to do it again. So I have 138.73 moles of water, just like I had before. My heat of vaporization is 40.7 kilojoules per 1 mole of water. My moles cancel out. I end up getting another very large number, 138.73 times 40.7. So I have, this is the highest, this is the most energy of any part of this, 5,646.31 kilojoules. That is a very high number, but remember, you're breaking apart all of those hydrogen bonds in water. Water, which likes to stick to itself because of hydrogen bonds, you need to break that stickiness, which means you need to put a lot of energy into this in order to make that happen. For 1 mole of water, it's 40.7 kilojoules. 2 moles of water, 81.4 kilojoules. 138.73 moles of water, 5,646 kilojoules. We're still not there yet. We have water vapor at 100 degrees Celsius. We need to go water vapor at 100 degrees Celsius to water vapor at 180 degrees Celsius. So we have one more temperature change, one more specific heat problem, and it looks like I still have the space on my paper to make this happen. So again, delta H, we're assuming that no mass is lost. We're assuming the same mass of water the whole way through. So I have still 2,500 grams of water. I have a new specific heat for steam, 1.87 joules. And my temperature change now is 80 degrees. So now I go 2,500 times 1.87 times 80. So 374,000 joules, which would be 374 kilojoules. So what did I just do there? I calculated all of the energy required to raise 2 kilograms of ice at negative 40 degrees Celsius to water vapor at 100 degrees Celsius. Yes, it's a long, tedious process, but every step in this process is essential if I'm going to get the right answer. So now I have to add up all those energies. Once I have all those energies, I know how much energy is required to make this happen. And then I can go back to my heat of combustion for ethanol and actually get this to proceed as it should. So I have 206 plus 835.15 plus 1045 plus 5646.31 plus 374. My total amount of energy required is 8,106. Total energy required is 8,106. Now again, this is using way too many significant digits. I'm not really allowed to use that many significant digits, but if I want to round that off at the end, that's probably the best strategy. I'll get slightly more accurate numbers if I continue to use the proper amount. So now, that is how much energy I need to make this process happen. Where is the energy coming from? I'm burning ethanol. So ethanol is C2H5OH. How would I put this in a balanced equation? Oxygen, and then I'm combusting, so good old combustion produces CO2 and H2O. Now, if I make this the way I think it should be, I would have 2 carbons, 2 carbons. This would be 3 hydrogens, or I'm sorry, 6 hydrogens, 6 hydrogens. I have 3 oxygens. I have 3 oxygens. Now if I make this a 2, does that get me where I need to be? No, but maybe a 3. So I have 9 oxygens over there. Now I have, trial and error. Now I should have 8, 9. Here I have 4, 7. Uh-oh. So I was right the first time. Yeah, this is the tedious part about balancing. So now I have 6, 7, 3, and 2. That's 7. So 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens, 1 plus 5. Crap. Now I should be right. Ah, no, it was right. Ay, ay, ay. Okay, 3. I was right the first time. This is why we double check and triple check and quadruple check. But you know what I'm going to find out? I don't even need to do this. But 2 carbons, 2 carbons. 6 hydrogens, 6 hydrogens. 1, 2, 3, 4, 5. Why am I looking at this wrong? 3, 4, yes, okay, so that is right. 1 plus 6 is 7. 4 plus 3 is 7. Okay, thank goodness, all balanced. But guess what? I actually don't need to find that because the other thing I'm adding in is heat. This is an exothermic reaction. Heat is coming out. For 1 mole of this, I'm producing 1,360 kilojoules of energy. Half a mole of this, half a mole of that. 2 moles of this, 2 moles of that. I have that much energy. Now I have to take that energy and convert it into moles. Does it really matter that I have a balanced equation? No, because I told you this is the molar heat of fusion. I'm sorry, molar heat of combustion. That's a mole. That's how much I get out of a mole. So I really only have to do a conversion here where I have my required energy, 8,106.46 kilojoules. And now I'm going to convert those kilojoules into moles of ethanol. So 1 mole of ethanol would be 1,360 kilojoules of energy. My kilojoules cancel out. I end up getting 5.96 moles of energy. I'm sorry, moles of ethanol, right? Because this is moles of ethanol. So 0.596 moles of ethanol are required in order to get enough. That's the minimum amount of ethanol I would need to get that much energy. Now, this particular problem does not specify what sort of units I need for ethanol. If I gave it in moles and I'm not specifying, that's okay. However, you can never measure moles on a scale. You can never count number of particles. We don't have enough time in the universe probably to count a mole. So what we can do instead is just take moles and put it into grams just to make things a little neater. So I have 2 carbons, which is 24, plus an oxygen, plus 6 hydrogens. It's 46 grams. So 46 grams over 1 mole. Let me double check. 24 plus 16, that's 40, and then 6, 46. Okay, so I end up having 274 grams of ethanol. Now would be a good time to turn that back into turn that back with consideration of significant digits. My original problem had 2 significant digits, so I'm basically talking about 200, I don't like mechanical pencils, 270 grams, 270 grams of ethanol. That would be the best answer I could give, because I can weigh that on a scale. What's the minimum amount of ethanol? Now realize, when we did our lab where we saw how what we calculated as the molar heat of combustion was far lower than the actual heat, because we have heat radiating all around. You would have to transfer all of this heat into the water. Now if you burn the ethanol inside a chunk of ice and you had an adequate amount of oxygen, well then that would be the minimum amount of ethanol. That should be able to take all of that ice and turn it into water vapor at 180 degrees Celsius. But that's the minimum amount of ethanol that would release the minimum amount of energy, or the amount of energy we need. Would you actually need more than that? Probably. You can't expect every single atom or every single molecule of ethanol to combust. So you really would need a little more than that, but it says what is the minimum amount of ethanol. With that, we have settled, and we've gone through a 6-step problem, which is pretty darn impressive. I'll look at the last problem on a separate video because I want to make sure I'm not using up all of my disk space with this one particular video. But this is a 6-step problem. You need to think your way through it. We're looking at the specific heat, we're looking at the molar heat of fusion, molar heat of vaporization. We get a total amount of energy, and then that energy we convert into moles of our product, moles of our combustible liquid in this case, or moles of any fluid or any gas that we're going to burn, or any solid for that matter, any solid we're going to burn in order to get all that energy. Multi-step problem, Looks complicated, but if you break it down into steps, it is manageable. We'll see the next video, which is a ridiculous video that you saw at the beginning of the year. We'll see that, but don't expect this last one on the test. I just wanted to kind of bring things full circle. This you will need to know for the test, however. So, good luck.